New pictures captured by the James Webb Space Telescope have staggered scientists. Instead of extending our impression of the universe, these photos revealed an unsettling reality. Our current understanding is lacking, and we struggle to grasp the full extent of the universe in its early stages. Theories about the universe's origin are now being pushed to their limits, prompting new speculations about its formation. The central question arises: how was the universe formed, and why? This discovery challenges even the most experienced astronomers in understanding the Big Bang and its ongoing complexities. It leads us to re-evaluate the Big Bang theory itself. Contrary to popular belief, the Big Bang was not an explosion within pre-existing space. Rather, it was space itself that began expanding around 13.8 billion years ago, along with matter and time. This idea relies on a unique characteristic in physics and cosmology, a phenomenon where gravity is so strong that space-time curvature becomes infinite. Today, billions of years after the universe's beginning, we understand that our cosmic home is part of a vast, dynamic interaction. For scientists, this reveals a fundamental piece of the universe's existence: its continuous evolution. The universe is not moving through pre-existing space, but rather, space itself is constantly expanding. According to conventional theories, the first stars began to shine 200 to 300 million years after the Big Bang, marking the end of the so-called Dark Age. This was when the first luminous celestial objects clustered together to form mature galaxies. However, the speed at which these early galaxies developed remains an ongoing mystery. A significant piece of information emerged from the first images captured by the James Webb Space Telescope in July 2022. Researchers announced that the telescope had detected various galaxies, some of which existed only 300 million years after the universe's formation. Compared to galaxies that formed billions of years later, these early galaxies were significantly smaller and less massive, which aligned well with scientific models. The density of matter in the early universe was seemingly insufficient to form galaxies the size of those we observe today. However, the discovery of 6 astonishing redshifted light sources from the James Webb Telescope triggered one of the most significant astronomical crises in recent years. These newly discovered galaxies, although similar in age to previously recorded ones, are nearly as massive as our own Milky Way galaxy. This presents a fascinating mystery in cosmology. By examining a series of images taken by the near-infrared camera, researchers identified the light sources using redshift. They confirmed that the light from these objects took over 1 billion years to reach us, indicating these galaxies formed 570 to 700 million years after the Big Bang. Remarkably, these galaxies were so massive that they defied conventional cosmological assumptions. Instead of the expected dwarf galaxies, the structures identified were almost as large as the Milky Way. Further analysis revealed that these galaxies were already gravitationally bound collections of stars with masses exceeding 10 billion times that of the Sun. One of them could even be as massive as 100 billion solar masses. If this possibility is accurate, the mystery remains unresolved. Even in this scenario, there would be significantly more mass in the early universe than previously expected, introducing a paradox to our understanding. These objects challenge nearly all standard cosmological theories. If even one of these galaxies proves to be real, it would fundamentally challenge past assumptions about the formation of early galaxies. Furthermore, the density of matter in the early universe would need to be several times greater than previously accepted to explain this phenomenon. One alternative explanation suggests that these galaxies formed in an entirely unknown manner, further complicating the cosmological picture. These discoveries and subsequent discussions are likely to lead to further evaluations of the Big Bang theory. Many space scientists, especially those with alternative perspectives, are frustrated and often find their viewpoints overlooked in scientific journals. Even those who express doubts about existing theories are frequently labeled as eccentric. However, it is clear that even proponents of the Big Bang theory are regularly confronted with unanswered questions. These include: why and how did something literally emerge from nothing 13.8 billion years ago? Could something have truly arisen from nothing, or was there some triggering event? Was it all an accident? Stephen Hawking noted that the concept of time, as we understand it, began with the Big Bang. Thus, this process could not have been triggered by an external cause. A similar question involves the uniformity of radiation and matter distribution throughout the universe. Regardless of direction or distance, we observe similar densities and distributions of galaxies, nebulae, and radiation. Current theorists explain this phenomenon with the theory of cosmic inflation. However, some researchers have expanded this assumption with the theory of chaotic inflation, suggesting that inflation has only stopped in specific regions, like bubbles, while continuing infinitely in others. This raises the possibility of multiple universes forming in these bubbles, each governed by its own physical laws. In this model, an inevitable question arises. What if our universe does not represent the total whole? What if another universe existed before ours? In this case, the Big Bang could be part of a larger cyclical pattern. Our universe would then be part of a greater, more complex structure. According to this view, there could be an eternal cycle of collapse and rebirth. However, this is not the only perspective in cosmology. For instance, an article published in 1955 by NASA's Big Think suggested that the universe may never have experienced a Big Bang and instead could have existed for an infinite period. In this view, the expansion of the universe would be non-existent, and the continuous evolution of matter could give the illusion of constant growth. Another intriguing and controversial hypothesis emerges from quantum physics and string theory. Some studies suggest that our universe and everything within it could be a projection or a higher dimensional simulation. While this may sound like the premise of a science fiction film, it could be connected to the Kessler scale, which measures a civilization's ability to harness energy. If a Type 3 civilization were capable of utilizing the energy of an entire galaxy, it could create a perfect simulation. However, confirming the reality of such a hypothesis is highly complex and speculative. Exploring the depths of cosmology and the origins of our universe leads us into profound mystery and ongoing scientific inquiry. The new images captured by the James Webb Space Telescope have reignited debates about the very fabric of reality, challenging established theories and prompting scientists to reconsider fundamental aspects of cosmological understanding. At the heart of this inquiry lies the Big Bang theory, a cornerstone of modern cosmology. According to this theory, approximately 13.8 billion years ago, the universe emerged from an extraordinarily dense and hot state, rapidly expanding to form the space-time and matter we know today. This monumental event wasn't just an explosion within pre-existing space, but rather the beginning. Surprisingly developed and massive compared to current cosmological models. One of the key questions raised by these discoveries is the nature of cosmic inflation. According to the prevailing theory, inflation occurred in fractions of a second after the Big Bang, causing the universe to expand dramatically. This rapid expansion explains the uniformity of cosmic microwave background radiation observed across the universe today. However, the current discoveries suggest complications in the early universe's evolution, which may require adjustments to inflationary models. The formation of galaxies like those observed by the James Webb Telescope forces cosmologists to reconsider the conditions and processes governing the universe's early history. These galaxies, massive and mature so shortly after the Big Bang, suggest that the density of matter was much higher than previously estimated. The mystery deepens when we consider how such enormous structures could form and evolve in such a short time. Additionally, the discovery of these galaxies raises questions about dark matter and dark energy, two elusive components that make up most of the universe's mass and energy content. While dark matter is believed to provide the gravitational framework essential for galaxy formation, the distribution and properties of dark matter in the early universe remain uncertain. In line with these astrophysical mysteries, theoretical physicists are exploring alternative cosmological models that challenge the standard Big Bang perspective. Some theories propose that our universe is just one of many in a vast multiverse, each with its own physical laws and constants. These ideas, emerging from advances in string theory and quantum cosmology, suggest a more interconnected universe than previously imagined. One theory gaining traction is eternal inflation, where universes continually emerge from a larger inflating cosmos. In this eternal inflation model, the bubbles of universes may form in isolated pockets of spacetime, each with its own unique properties. This leads to the tantalizing possibility that our universe is merely one of countless others, each following its own set of physical rules. Such a multiverse framework could provide explanations for anomalies and mysteries that seem irreconcilable with the standard Big Bang model. Another perspective challenges the very premise of a beginning. The cyclic universe model proposes that our cosmos undergoes infinite cycles of expansion, contraction, and rebirth, negating the need for a single moment of creation. In this scenario, the Big Bang is not the absolute beginning, but simply the latest phase in an eternal series of events. Proponents of quantum cosmology add yet another layer of complexity. Some researchers suggest that the universe could be a product of quantum fluctuations in a pre-existing void. In this view, the laws of quantum mechanics allow for the spontaneous emergence of spacetime and matter, making the concept of nothingness more ambiguous than previously thought. Further complicating our understanding is the role of dark energy, the mysterious force driving the accelerated expansion of the universe. Dark energy, which makes up roughly 68% of the universe's energy content, remains poorly understood. Could this enigmatic force also influence the formation of early galaxies? If so, its properties might need to be redefined, along with our understanding of spacetime dynamics. The James Webb Space Telescope's discoveries underscore the need to reassess fundamental cosmological assumptions. The sheer mass and rapid development of these early galaxies suggest that our models of galaxy formation, dark matter distribution, and the timeline of cosmic evolution may be incomplete or flawed. Some cosmologists advocate for radical approaches, suggesting that our understanding of gravity itself might require modification. Theories such as modified Newtonian dynamics, MOND, or emergent gravity challenge Einstein's general relativity, proposing alternative frameworks to explain large-scale cosmic phenomena. Meanwhile, the possibility that we are living in a simulated universe continues to captivate both physicists and philosophers. If our universe is indeed a projection or simulation, it would redefine not only cosmology but also our place in existence. Such a hypothesis, though highly speculative, forces us to consider the limits of human perception and technological capability. As scientists analyze data from the James Webb Space Telescope and other instruments, they confront profound questions about the origin, structure, and ultimate fate of the universe. These revelations are not just challenges to establish theories, but invitations to explore deeper truths about reality itself. The journey of discovery is far from over. Each new observation, theory, and debate takes us closer to understanding the cosmos. Whether through the refinement of existing models or the development of revolutionary ideas, humanity's quest to unravel the mysteries of the universe continues to inspire and amaze. As new data from the James Webb Space Telescope, JWST, continues to be analyzed, the implications for cosmology grow even more profound. The discovery of massive, mature galaxies so soon after the Big Bang challenges not only the timeline of cosmic evolution but also raises broader questions about the underlying principles of astrophysics. For instance, if the density of matter in the early universe was indeed higher than previously assumed, it could force revisions to the standard lambda-CDM model, which describes the composition and evolution of the cosmos. This model, incorporating dark matter and dark energy, has been the cornerstone of cosmological research for decades. However, the unexpected maturity and size of early galaxies suggest that additional mechanisms or components may need to be integrated into our understanding. Reassessing dark matter. The role of dark matter in early galaxy formation is now under intense scrutiny. Dark matter, though invisible, exerts gravitational influence and is thought to have acted as a scaffolding for galaxy formation. If early galaxies were more massive than predicted, it may indicate that dark matter behaved differently in the universe's infancy, or that its properties are more complex than previously believed. Some researchers propose that dark matter might interact with itself or with regular matter in ways not yet observed. Alternatively, these findings might hint at the existence of yet undiscovered particles or forces, pushing the boundaries of particle physics and cosmology. The nature of cosmic inflation. The theory of cosmic inflation, which describes the universe's rapid expansion fractions of a second after the Big Bang, also faces new challenges. Inflation was introduced to explain the uniformity of the cosmic microwave background radiation and the large-scale structure of the universe. However, the discovery of massive early galaxies complicates this narrative. Did inflation proceed differently in localized regions of the universe, leading to denser pockets of matter where massive galaxies could form? Or could these findings hint at a more complex or prolonged inflationary period? Such questions are now at the forefront of theoretical physics, prompting new models and simulations to test these ideas. The question of fine-tuning. The James Webb discoveries also reignite debates about the so-called fine-tuning of the universe. The precise conditions required for galaxy formation, star development, and ultimately, the emergence of life suggest that the universe's laws and constants are finely balanced. Some interpret this fine-tuning as evidence for a multiverse, where countless universes with varying physical laws exist, and ours happens to be one where conditions allow for complexity and life. Others see it as a potential indication of deeper, unknown principles governing the cosmos, principles that might unify quantum mechanics and general relativity into a single, coherent framework. Future exploration. As JWST continues its mission, scientists eagerly anticipate further revelations. Upcoming observations will delve deeper into the early universe, potentially identifying even older and more massive galaxies, probing the formation of the first stars, and examining the environments where black holes may have formed. Additionally, new instruments, such as the Square Kilometre Array, SKA, and next-generation gravitational wave detectors, will provide complementary insights. These tools may uncover clues about the very first moments after the Big Bang or detect the elusive signals of dark matter and dark energy. Philosophical implications. Beyond the scientific challenges, the findings from the James Webb Space Telescope have philosophical ramifications. They compel us to question our place in the universe, the nature of reality, and the limits of human understanding. Are we capable of fully comprehending a cosmos so vast and complex? Or are there aspects of existence that will forever remain beyond our grasp? As scientists and thinkers wrestle with these questions, they underscore the importance of curiosity and the pursuit of knowledge. Conclusion. The discoveries made possible by the James Webb Space Telescope represent a turning point in cosmology. They challenge long-held beliefs, inspire new theories, and open doors to realms of inquiry previously unimagined. As we continue to explore the cosmos, each revelation reminds us that the universe is not only stranger than we imagine but stranger than we can imagine. In this grand journey of discovery, the pursuit of understanding becomes a testament to the resilience and ingenuity of the human spirit.